Hello guys. So today I'll talk about chapter 4.1 OLS asymptotics. Quick reminder before we start, everything we did in the last chapter, inference, right? T-test, F-test, confidence intervals, all of that relied on normality of mu. One of the CLM assumptions. What is CLM? Classical linear model assumptions, okay? But we also said normality is not guaranteed and it often fails in real data. So here's the natural question. What happens to our test if mu is not normal? That's exactly what this chapter answers, okay? The keywords is asymptotics. What does it mean? It means that what happens as the sample size gets large, okay? We'll see that even without normality, our usual T statistics and F statistics still work fine, approximately, okay, as long as we have enough data. Think of it this way, chapter 3, inference, give us exact results, but only under strict assumptions, including normality. Chapter 4.1 gives us approximate results, but under much weaker assumptions. This is why it's so useful in practice, since real-world data really looks perfectly normal. All right, so let's go slide by slide and build this properly. Let's organize what we know and what's new. So far, everything we've done falls under properties that hold for any sample size, right? Any sample size like n equal 10 or n equal 20. Unbiasedness, right? The first one, unbiasedness under MLR 1 through 4. And then we have our variance formulas under MLR 1, 3, 5. Next one, Gauss-Markov theorem, which means OLS is blue under MLR 1 through 5. And then exact sampling distributions, t-test, f-test, right, under MLR 1 through 6, which here includes normality, right? Notice the strongest results always needs normality. Now, new category, properties that only hold in large samples, but here's the key advantage, right? We drop the normality assumption entirely. So, you see here, large samples. There are two new concepts today. The first one, consistency. Consistency under MLR 1 through 4, which means no normality needed. Next one, asymptotic normality, right? Okay, tests under MLR 1 through 5, still no normality needed. This is the whole point of this chapter. Even if mu is not normal, if our sample is large enough, our estimator still behave well and our UUT test, F test still work, okay? Just approximately, okay? Approximately, not exactly. That's why this matters so much in real applications where normality is often questionable. Okay, let me add one page to show you what is the difference between consistency and asymptotic normality. Okay, what it means and what is the key law behind it. The first one, consistency, it means that more data closer to true parameters. Okay, more data closer to truth. The law behind it is law of large numbers. Okay, which is LLN, okay, law of large numbers. Next one, asymptotic normality. It means that large sample, we will have normal distribution of beta gen hat. The law is, okay, central limit theorem. Okay, don't confuse about those two, right? The first one, consistency, because of law of large numbers. Asymptotic normality because of central limit theorem. In the real world, we almost never have perfectly normal errors, but we often have large samples. Asymptotic, it is what makes OLS inference practical and robust in applied economics. Okay? The first concept, consistency. Let's build the intuition before the formula. Let's see the definition. An estimator theta n is consistent if, okay, as n goes to infinity, the probability that theta n is within epsilon of the true theta goes to 1 for any epsilon, okay, for any arbitrary epsilon, however small. Okay, in plain words, it means that as we get more and more data, our estimate gets closer and closer to the true value, and we can make this as close as we want by collecting enough data. All right. So alternative notation, you will see plim theta n equal theta. Plim means probability limit. This just means the estimate converges to the true value as n grows. Okay? Let's compare it with unbiasedness, okay? That's a different property, okay? Unbiasedness says, on average, across many samples, we get the right answer even in small samples. This is unbiasedness. But for consistency, consistency means something else, okay? With enough data, we get arbitrarily close to the right answer, even if in principle we were biased in small sample. Consistency means that the probability that the estimate is arbitrarily close to the true population value. All right. And let's see the last point. Consistency is a minimum requirement for sensible estimators. And this is an important framing. Consistency, okay, it's a minimum requirement. If an estimator isn't even consistent, meaning more data doesn't help you get closer to the truth, it's basically useless. We've never seriously used it, no matter how appealing it looks otherwise. Okay, without consistency, we'd never use it. Now let's state this formally for OLS, which is theorem 5.1. Under MLR 1 through 4, the same conditions were used earlier for unbiasedness, right? OLS is also consistent, which means plain beta j hat equal beta j for every coefficient. Let's look at a simple case to build intuition. Okay, so we have a simple regression, one x variable. So the plain beta 1 hat equal beta 1 plus covariance of xi mu over variance of x1. x1, okay, because here is simple regression, so we only have x1. This formula tells us exactly when consistency holds. If covariance of x1 mu equals 0, okay, if this one, if this one equals 0, meaning x1 and mu are uncorrelated, all right, uncorrelated, then the extra term vanishes, all right? So if this one equals 0, this term gonna disappear, right? That means plain beta 1 hat equal beta 1 exactly, which is consistent. But, all right, but if x1 and mu are correlated, we get a permanent bias term that does not shrink as n-go grows. More data won't fix it. This leads to a slightly weaker version of our exogeneity assumption, which is MLR4 prime. Okay, this is the prime. Expected value of mu equals 0 and covariance of xj mu equal 0 for all j, which means all x are correlated with mu. If we compare this to the original MLR4, do you still remember? Okay, this is the prime. This is the original MLR4. which means zero conditional mean, right? Notice that MLR for prime is weaker. Zero conditional mean is a very strong statement. It says mu is unrelated to x in every possible way. Zero correlation only results out. Again, zero correlation only rules out linear relationships between x and mu. Right? So this is weaker, which means MLR 4 prime. So consistency only requires this weaker condition, okay? Consistency only requires this weaker condition, which is zero correlation, not zero conditional mean. Okay, let me write it down. This one is zero correlation. Not the full zero conditional mean assumption. This is exactly why consistency is easier to achieve than unbiasedness. Okay, again, consistency is easier to achieve than unbiasedness, and why it becomes our fallback tool when the stronger assumption fails too demanding. Let's connect this to something we already know, okay, omitted variable bias, but now in asymptotic term. This one I just mentioned to you, right? For consistency of OLS, only the weaker MLR4 prime is needed. Next one. We're talking about omitted variable bias in terms of asymptotic. So suppose we have the true model, which is y equal beta 0 plus beta 1 x1 plus beta 2 x2 plus v. And suppose we misspecify, okay, we drop x2, we put it into the error term, which means y equal beta 0 plus beta 1 x1 plus mu. All right, so basically we drop x2 and we put it into the error term. Now, using our consistency formula from the last slide, okay, from last slide. So here we have plane beta 1 tilde equal beta 1 plus covariance x1 mu over variance x1. And then we substitute mu equal beta 2 x2 plus v, right? Okay. We substitute mu equal beta 2 x2 plus v and work through this covariance. So we have beta 1 plus beta 2 times covariance x1, x2 over variance x1 equal beta 1 plus beta 2 delta 1. Okay? Where delta 1 equals covariance x1, x2 over variance x1. Let me help you. Okay, this blue part is delta 1. Okay, delta 1 equals covariance x1, x2 over variance x1. This is exactly the slope you would get from regression x2 on x1. Okay, same formula as the exact omitted variable bias result from chapter 2, just now expressed as plain an asymptotic large sample statement instead of an exact small sample one. So here, you see, there's no omitted variable bias if the omitted variable is irrelevant or uncorrelated with the included variable. What does it mean? It's the same intuition as before, okay? There's no bias, even asymptotically, if either beta 2 equals 0, which means x2 is irrelevant. Okay, so the omitted variable truly doesn't matter, which means beta 2 equals 0, or covariance x1, x2 equal 0, which means x1 and x2 are uncorrelated. So you see here, more data does not fix omitted variable bias. Again, more data does not fix omitted variable bias. Since this bias lives in the plane itself, it's baked into the limit. Collecting a bigger sample won't make it go away. This is different from problems that shrink with sample size. Omitted variable bias is a permanent problem caused by model misspecification, not a small sample fluke. Let me write it down. Okay, keep it in mind. More data does not fix omitted variable bias. And I want you to look at this bias term. Okay, let me add one page. Okay, something wrong with my computer again. Please bear with me. I'm gonna fix it. I'm still here. Just let me restart my computer. Okay, let me open my Zoom. Zoom, okay. All right. Okay, okay, so I'm back again. Let me continue. Make sure it's still recording. Yes. Okay. Okay, so here I want you to look at the bias term, which is beta 2 delta 1, right? Let me see. It's beta 2 delta 1. Let's see the direction of the bias. This is the bias term, right? Beta 2 delta 1. What is beta 2? And what is delta 1? What is beta 2? It's the effect of x2 on y. Right? And for delta 1, it's the correlation between x1 and x2. So let's see the direction of bias. This is where it gets practically useful. We can sign the bias without running any regression. So we have beta 2 and delta 1, which equals covariance of x1, x2 over variance of x1. Okay, let's see the bias. And let me compare beta 1 delta versus beta 1. Right? So let's see if both beta 2 and delta 1 are positive. So the bias will be positive, right? And beta 1 delta, of course, will be overestimate. How about if beta 2 is positive, but delta 1 is negative? So the bias is negative. Okay, so here will be underestimate. The other way around, suppose a beta 2 is negative, delta 1 is positive. Okay, so its bias is negative and underestimate. And the fourth situation, both beta 2 and delta 1 is negative. So the bias is positive, right? So we have overestimate. Okay, so just clarify the bias term. Next one. Now the second big concept, asymptotic normality. This is the result that really rescues us from the normality problem. Okay, let me recap. In practice, MLR6 is often questionable, right? As I mentioned earlier, which is normality, is questionable. If it fails, our exact t-ratio f-test from chapter 3 could technically be wrong. But here, the good news, and it's the main message of this slide. T ratio and f-test still work fine as long as the sample size is large enough. Okay, and more than that, OLS estimates themselves becomes approximately normal in large samples, even without assuming MLR6 at all. That's why this is formalized in theorem 5.2 under MLR1 to 5. Notice, not MLR6, okay? We don't need normality here. Beta j hat minus beta j over the stand error of beta j hat is approximately normal distributed with mean 0, variance 1 in large sample, okay? And also plane sigma square hat equal to sigma square. Here means approximately, okay? Approximately. Let's compare this to theorem 4.1 from last chapter. Same looking formula, but there it was exact, okay? There is what exact. And it required normality. I mean, for theorem 4.1, let me get back to you. Okay, here, theorem 4.1, normal sampling distribution. Let me copy it. All right. So for theorem 4.1, it was exact, okay, exact. And it requires normality. But here, theorem 5.2, it's only approximate. All right, you see A here, which means approximate. But it holds under much weaker conditions, okay? This is the trade-off. Also worth noting, plane sigma hat, sigma square hat equals sigma squared. Our estimator of the error variance is also consistent. Okay, it's also consistent. As long as you see plane, it means consistent. This is why, in practice, econometricians don't worry too much about normality. As long as you have a reasonably large sample, your U, your T ratio at test, and confidence intervals are still approximately valid. Again, approximately valid. Okay, let's wrap up with the practical takeaways of asymptotic normality. In large samples, okay, the t distribution is close to the normal distribution. And here is the standard normal. That's why the rule of thumb we memorized, okay? The critical value 1.645, 1.96, and also 2.576 work so well in practice, even though technically they are normal critical values, not t critical values, okay? But in large samples, t distribution is close to the standard normal. consequence. Okay, t-test, confidence interval, f-test are all valid in large samples, even without MLR6. This is the payoff of everything we've built today, but important warning, don't skip this. All right. MLR1 through MLR5 are still required, necessary, especially homoscedasticity. MLR5 asymptotics rescues us from the normality assumption, but not from the other assumptions. If those fail, we still have problems. That's a topic for later chapter. Okay, so quick look at why variance beta j hat, variance hat or beta j hat behaves nicely as n grows. Okay, so we have this formula: variance hat beta j hat equals sigma square hat over SSTJ times 1 minus RJ squared, right? Because sigma square hat convergence to sigma square, the true error variance, and SSTJ grows roughly proportional to n times variance xj. It keeps growing as we add data, okay? It keeps growing as we add data. Another one, RJ square convergence to some fixed number, reflecting how correlated xj is with the other x, right? So if we put them together, as n grows, the denominator grows. So variance hat beta j hat shrinks towards 0. Our estimates get more and more precise. This is exactly the mechanism behind consistency and asymptotic normality. More data literally squeezes the sampling variance down, which is why our estimator homes in on the true value. Okay, let me write it down. As n grows, this part grows, which means variance beta j hat and hat shrink towards 0. Okay? If it shrinks towards 0, which means our estimates get more and more precise. All right, so more data squeezes the sampling variance down. More data squeezes the sampling variance down. Let's put a precise rate on this shrinking and see it with real numbers. So here we have variance hat beta j hat shrinks at rate 1 over n. Since SE is the square root of variance, okay, SE beta j hat shrinks with the rate square root 1 over n, all right? This is exactly why large samples are better but notice it's not a straight line improvement. Doubling your sample size doesn't cut your standard errors in half. Because of the square root, right? You need to quadruple your sample to cut SE in half. Okay? Diminishing returns, good intuition, right, from microeconomics, diminishing return. Let's check, okay, let's check this with a real example from birth weight equation, looking at SE on the 6, okay? So here the variable, which means cigarettes smoked coefficients. This is the full sample, okay, n equal more than 1000. So we have SE beta 6 hat equals 0.00086. And this is half sample. And then we have SE, which is 0.0013, right? So this is full, and this is half. And let's check, okay? Let's check the rate. Okay, we use this one from the full divided by the SE from the half. What we get? This one is approximately, okay, it's approximately equal 0.707. And indeed, okay, I think I need to write down one more step for you. Let's see here. This is the sample size, half of the sample size. This is the full. So basically, this equals square root 1 over 2. And this one is approximately 0.707. And indeed, if you compute this one, it's approximately equal 0.66, close to the predicted rate, okay? Confirming that square root 1 over n relationship in real data. All right, so let me finish this chapter by halving your sample size doesn't just add noise. It visibly and predictably inflates your standard error. Following this exact square root rule, okay, following this exact square root rule, this is the practical numerical payoff of everything we derived today, which is asymptotics isn't just abstract theory. You can see it directly in real standard errors. Let me finish it by writing. Okay, asymptotics isn't just abstract theory. We can see it directly in real standard errors. Okay, so that's the end of chapter 4.1. only 8 pages, right? Only 8 pages. And it's about asymptotics. Hope you enjoy this video and please review it. So as I mentioned before, we move the class to online, and actually I'm gonna send you this video link. All right, so basically we will see each other next month, which is 3rd of August. Please enjoy your holiday and don't forget to prepare for your exam. All right, so bye bye.